As the moon continued to accrete and grow, its interior underwent differentiation. Heavier elements sank toward the center, forming a dense core, while lighter elements migrated upward, leading to the development of the moon's mantle and crust. The heat generated by the intense collisions and the decay of radioactive isotopes within the moon's interior led to volcanic activity on its surface. Lava erupted from the moon's interior and spread across large areas, resulting in the formation of basaltic plains known as maria. Over time, the moon's accretion and volcanic activity subsided, and it entered a phase of relative stability. The moon's gravity remained sufficient to maintain its spherical shape, and its orbit around Earth became more regular. The collision that formed the moon had significant implications for Earth and life as we know it. Without the moon's formation, Earth's axis of rotation would have been less stable, leading to severe and chaotic variations in climate. The moon's presence helped stabilize Earth's axial tilt, creating a more predictable and stable climate regime that has been crucial for the development and sustainability of life. The giant impact hypothesis is supported by various lines of evidence. One compelling piece of evidence comes from the analysis of lunar samples collected during the Apollo missions. The isotopic compositions of these samples closely resemble those of Earth, suggesting a common origin. Additionally, computer simulations of the giant impact have been able to reproduce many of the moon's characteristics, such as its size, composition, and orbital dynamics. These simulations provide further support for the hypothesis and help refine our understanding of the collision and subsequent moon formation. The prevailing theory about the formation of the moon is known as the giant impact hypothesis. Approximately 4.5 billion years ago, during the formation of our solar system, a Mars-sized object, often referred to as Theia, collided with a young Earth. This event, known as the giant impact, is believed to have had a profound impact on the evolution of both Earth and the moon. The collision between Earth and Theia was an extremely violent event. The energy released during the impact was enormous, causing a catastrophic explosion. The immense heat generated vaporized Theia and a significant portion of Earth's mantle. The collision debris was ejected into space, forming a massive cloud of molten rock and dust. The debris cloud from the collision began to orbit around Earth due to the influence of gravity. It formed a disc-shaped structure known as a protoplanetary disk. This disk extended into space around Earth, with the central region being denser and hotter due to the higher concentration of material. Within this protoplanetary disk, collisions and interactions between the debris particles occurred. Over time, these particles began to accrete or stick together through mutual gravitational attraction. The process of accretion allowed the debris to grow larger and form protomoons. As accretion continued, larger and more massive protomoons started to develop. These protomoons underwent further collisions, merging with other protomoons and accumulating more material. The gravitational forces involved caused the protomoon to gradually clear its orbit, becoming the dominant gravitational force within its immediate vicinity. Eventually, the largest and most dominant protomoon, often referred to as the moon-forming impactor or Theia, emerged from the chaotic environment of the protoplanetary disk. Its growth and size surpassed all other protomoons, and it became the precursor to the moon we see today. The gravitational interactions between the protomoon and Earth played a crucial role in its evolution. The protomoon's orbit gradually stabilized, becoming more circular over time. The gravitational forces caused tidal effects on both Earth and the protomoon, dissipating energy and gradually slowing down the rotation of both bodies.